Hey, my name is Jonathan Helm, and in this video, I'll show you how to do a one-way ANOVA in R. So I'm just going to use the salary dataset, which is the same dataset that I've used for many of the videos in the YouTube channel. So the first thing I'm going to do is just read that dataset into R. Read the salary dataset into R. I use the read.csv function, and inside quotes I need to put both the path and the file name. So I'll grab the path. I'll also insert the file name. It's always a good idea to look at the first 6 rows of the dataset just to make sure everything was read incorrectly. Seems like everything's okay. Now, for this video, I'll look at mean differences of this variable salary across different levels of department. So department is a categorical variable, and it has 3 levels. Okay, so it takes on values 1, 2, and 3. Okay, so 1 is supposed to refer to individuals in the psychology department. 2 will refer to individuals in the sociology department, and 3 will refer to individuals from an economics department. Now, R doesn't know that this is a categorical variable yet, and one way that we can check that is by using a class function. So check variable, we'll call this a variable type, using the class function. So what does this mean? Well, let's look at the variable salary. So I can use class, and then I can do data $salary. And if I run this code, we're asking R kind of like, what type of variable is this? And there are a few different types out there, but we'll just talk about a few that are in this data set. One of the types is called numeric. And this maybe makes sense because if you look at salary, it seems like it's a numeric variable. The numeric means that, you know, it's a number, so it's a continuous variable, and it also has decimal points, right? So it has this decimal point here. If we look at the class of department, we get a little bit of a different answer. It says integer. So integer is still a numeric variable, right? So it's still a continuous variable, but it's only taking on integer values, so things that don't have a decimal point after them. So when R is telling us that this variable department is an integer, it's saying that it thinks this is a numeric variable, right? Similar to something like age. But if we're using an analysis of variance, we actually want to treat department as categorical. Okay, we want to treat it as categorical, so we want these to be different indicators of group membership. So what I need to do first, right, and you might run into this in practice, is we might need to change this variable to a categorical variable. And in R, a categorical variable is referred to as a factor. Okay, so let's begin by changing the variable department to be categorical. Now we'll do this by actually creating a new variable. So we're going to create a new variable in our data set, which will be the same as this variable department, except it'll become categorical. Okay, and this probably will become a little more clear, you know, once we have an example. So I'm going to say data $department factor. So this is going to create a new variable in my data set called data, and that variable will be called department factor. And I'm going to use the factor function, and inside that I'm going to put data $department. Okay. And then I'm going to add 2 more arguments. I'm going to put a comma here. I'm going to enter just to make some more space below so we can see this. And I'll say levels is equal to the values that are in that variable. So we just have a 1, a 2, and a 3. And then I'll have another comma, and I'll enter another argument, and I'll add labels. And now I have to create labels for each of these values. So in quotes, I'm going to put psychology, because psychology is what is referred to by the 1. I'm going to put a comma here, and I'm just going to put a carriage return so I can fit all the code on one space so you can see it, but you don't have to add that extra return. So I have psychology, sociology, and the last one is economics. Okay, in this parentheses, we'll close out this one, and then this one over here is going to close out the factor function. So what we're communicating to R is we'd like to take the variable called department in the data set called data, and we'd like to change it into a categorical variable, or in R language, we'd like to change it into a factor. We're saying that there are 3 levels called 1, 2, and 3, and we want to give those levels labels. We want to call it psychology in quotes, sociology in quotes, and economics in quotes. So if I highlight and I run this code, and then I take a look at the top of the data set again, right, you can see that I'm getting a new variable now called department factor. And you can see that it's mirror imaging what we have under this variable department, except now that we have labels for each of those values. So 2 is sociology, 1 is for psychology, and 3 is for economics. Okay? And so now I can use this variable in an analysis of variance. So in a similar way, we could have done this for the variable female. So if we wanted to create a new variable, we could call it something like sex or biological sex. And we could have the values 1 equal female and 0 equal male. And just to kind of finish up, now I'll take a look at the class. So I'll say class of data $department factor. And when I run that, we can see that R knows that this is now a factor, which means that R knows that this variable is a categorical variable. And so we can use that in our analysis of variance. Okay, so I'm going to move on to analysis of variance now. Now, one thing that I want to start off with is what R will do underneath the hood is it's going to take this variable and it'll translate it into kind of a series of numeric values. And these aren't the same as the 1, 2s, and 3s here. And we haven't talked about this much so far, and I won't spend a lot of time in the video talking about it because it's a little more in depth than I want to get into. But there are different ways to translate this information into a series of numeric variables. The most common way that we do that in psychology is through a method called effects codes. And when we use effects codes will test the hypotheses that we normally see in ANOVA. So normally from analysis of variance, we'll get main effects and interaction effects. Main effects and interaction effects, the way that they're normally interpreted, will correspond to an effect coding scheme, which is a particular way of translating this variable into a series of numbers. Okay, so we're not going to go through all of the ways in which we would do that, and we don't really want to do it by hand. So I'm just going to tell you a quick shortcut. So to make sure we are using an effect coding scheme, we have to add in this extra line of code. So it starts with options, open and close paren. And we'll type the word contrasts. We'll say equals. And we have 2 things that we need to insert in the vector. So we have contour.sum and contour.poly. And these ones need to both be in quotes. And you won't get any confirmation back, but essentially what we're communicating to R is we're saying if you run into a categorical variable and you need to assign or you need to use a particular coding strategy, this will guarantee that it will be an effect coding strategy. And we use an effect coding strategy because that will lead to the normal interpretations for main and interaction effects that we commonly use in psychology. Okay, so just kind of as a side note, SPSS uses this effect coding strategy by default, so you don't need to change anything in that program. But it's not the one that's the default in R. The default in R is called the dummy coding strategy. So again, kind of glossing over those details, I'm just going to go ahead and highlight and run this. And just make sure that anytime you're doing an ANOVA in R, that you start by adding that line of code. Okay, so now I can go on to my Way ANOVA. Now, there are many different ways and packages to do analysis of variance in R. I actually think that the best way to do it is through a specific package called car. So if you don't have the car package, then the first thing that we'll need to do is install that package. So to do that, we'll type install.packages, and then we'll write in quotes car, and then you can highlight and run this code. I already have the car package installed on my computer, so I'm not going to run that line of code in this video. But again, if you don't have it, you can just go ahead and run it. Now what we need to do to make the functions inside the car package available is to use the library function. So we'll do library and then car. And you'll notice this time that car is not in quotes. So I can highlight and run that. And now all of the functions that are inside of the car package are available for us to use. And the main one that we'll be using is called capital A for ANOVA. And we'll get to that in just a second. So to run the ANOVA, there's a two-step process. So step one is to, I was just going to call this to estimate the model. And then step two is to look at the results. So to estimate the model, it's actually going to look similar to a regression model. So I'm going to say model.01 is equal to LM. And then on the left-hand side, I'm going to have the variable that I'd like to predict. So I have salary, and that I will put that as a function of an intercept plus the factors that I'd like to use to predict it. So in this case, it's just department factor. So I type department factor. Okay, and those variables are in the data set called data. And I'll add this last line, NA action equals NA exclude. So what am I doing here? Well, we're communicating to R that we'd like to predict the salary variable using this factor. And these variables in the model are in the data set called data. And this last part is if you run into any missing values, so as you move down the rows of the data sets where you have salary and department factor, if any of those variables have a missing value for either salary or department factor, then just go ahead and remove that row from the analysis. Okay, so we'll highlight and run this code. And now the last part we need is to use the ANOVA function. So I'll do capital A and then NOVA. Okay, and this part's key. So this capital A ANOVA function is from the car package, and this one's different than a lowercase ANOVA function. So this function is different than this function, so make sure you're using the one with a capital A. We'll insert the model.01 here. Right, this is the model for the results that we'd like to look at, and then we're going to add this type is equal to 3. Now, again, I'll just add another little brief aside. There are different ways to do analysis of variance, and the different ways are called examining different types of sums of squares. So if you're interested in what those are, you can look those up. In psychology, we virtually all use a type 3 sums of squares, and this is what SPSS will do by default. Okay, so there are different other types of sums of squares, and they will give you, or they can give you, different answers from type 3. So we'll just use type 3 because that's the most common way, and again, I'm going to gloss over those details as well. So if I highlight and I run this code, you'll see that I get some results back. We're not interested in the intercepts. That's usually not an effect we're interested in. Instead, we're going to look at this department factor, right? And this is it's testing for the main effect of factor. So it's testing for the main effect of department. So remember that in this case, the null hypothesis is that the mean for psychology is equal to the mean for sociology, which is equal to the mean for economics in the population. So if that null hypothesis is true, then this p-value represents the probability of getting this sample effect or something more extreme. So if in the population those three means really are equal to each other, this is the probability of getting this sample result or something more extreme. And so in this case, our p-value is about 0.18, right? And kind of following convention, we would not reject the null hypothesis in this case. So this p-value is larger than 0.05. P-value is smaller than 0.05, then we would say that the probability of getting this result or something more extreme is less than 5%, and then we would usually reject the null hypothesis and conclude that at least one of the means is different from the others. Okay, but again, we don't know which specific means would be different in that case. We just know that at least one is different from the others. Okay, so that's all I have for this one. That's how you do one-way ANOVA in R. Again, I can't emphasize this enough. Make sure you include this line of code whenever you're doing analysis of variance in R. And make sure that you're using the car package to do type 3 sums of squares. It's really easy to miss those results, and you can get really different answers which don't correspond to the main and interaction effects that we normally test in psychology. Okay, thank you so much for watching.